Hello, welcome to today's lecture. First of all, I hope you all had a great recess week. Did something nice or like studied lecture notes. I don't know what you've been up to. In any case, so today is the last lecture that I will be teaching. Next week, Semi will take over. We will see each other next week again in the midterm. Maybe I'll say something regarding the midterm at the end of this lecture. But yeah, so this will be the last lecture from my side. What we're going to do today is I'm starting with a recap for the brief recap for the PDE methods for Black-Scholes, and the goal is to tie the PDE methods, Black-Scholes framework, to the Monte Carlo methods that we've introduced last week, which sort of were falling out of place. There was no connection to quant finance. The connections will appear this week. So we will see the risk neutral pricing formula in particular. Right. So I'll start with a brief recap. Then we're going to do that, and probably we're going to, depending on how fast I am, we're going to finish with this part before the break. And at the end, I thought what I'll do is I'll give you a short summary for the first 7 weeks, those that I taught, with the most important concepts, and then you can also ask questions, and I'll try to answer them, and sort of to wrap this first part, the theory part of this course. And I can also say something, or yeah, we can also discuss the midterm. Maybe that's important. Okay. So what's I think it was week 4 even. In week 4, we introduced the Black-Scholes framework, and in particular, we derived the Black-Scholes partial differential equation. It's this famous formula, where just that everyone is on the same page. V always depends on 2 parameters, t and x, sometimes t and s. That's just a way of writing it. And V is the price process. At the terminal time, so V capital T was just equal to our option, or the value of our option at state x. Yeah. And this price process evolves backward in time, and we're interested mostly in the value of V at time t equals 0, the present value of this option at maturity. Now, this was very general. This applies to all sorts of options, call options, put options, actually, or even American options. I'm not sure if we discussed this in details. If you've done this in the exercise sheet, I really forgot. If not, then essentially you have in the dynamic programming binomial tree exercise. The same thing is true for this Black-Scholes framework. So this is a very, very general, broad framework. There are PDE methods, which that's them. Okay. There are PDE methods. We have seen several of them: forward, or implicit, explicit, and mixed schemes that have all sorts of properties. They converge, all they converge. Some of them are more stable, some of them are less, have a better rate of convergence. But in any case, all of this works very well. But the crucial point is this only works in low dimensions. Low dimensions here means that the stock, or we're actually having options on a single stock, 2 stocks, maybe 3 stocks, but certainly not on a basket of 10 stocks. Yeah? So whenever we're in this situation, these PDE methods simply, it's not that they converge slowly or are unstable. It's simply that they don't work at all. Even setting up this discretization step, if you think about it, if you discretize a 10-dimensional space, it requires billions and billions of grid points, more than the computer can store. So it's really even not possible to set it even up. So it's really limited to, 2 dimensions, 3 dimensions, 4 dimensions. You can still maybe set it up 5. It will convert very slowly, but it's still manageable. But everything above 10 dimensions, it simply doesn't work. So this is why we started, or why we last week introduced these Monte Carlo methods, because what will turn out that you can actually solve for the solution of this PDE. So for V, the price you're interested in, you can solve it or approximate it using these Monte Carlo methods. Okay? And what we've done last week is nothing related to PDEs. We've only done the following. So if you have a function f, say on 0, 1 or any other interval, we've figured out that, well, if you define an appropriate density, phi, and sample according to this density, just generate independent points with the distribution phi, and you compute this empirical sum, so just empirical average over the data you've generated, then this sum Sn will converge to, well, this guy, which is, if we choose phi cleverly, then it's exactly the integral that we wanted. Yeah. So another way of writing this is, of course, the expectation of g with respect to a random variable that has density phi. That was in the last lecture. Now, in order, maybe to continue this recap, in order to implement these Monte Carlo methods, the algorithm is extremely simple. Yeah, there's nothing to do there. The crucial bit was generate these random IID data with a given distribution. So it's clear that you can do it, well, for uniform distributions, the Python can do it itself, or Gaussians. But if you're interested in, well, log normal, log normal is simple. You can still do it relatively easily. But for general distributions, you still need to figure out a big part of this process of Monte Carlo methods, go into figuring out how to generate these random samples with the given distribution. Yeah? And we've seen several methods. Inverse transform, most importantly, that was the simplest one for one-dimensional densities, and other methods like acceptance, rejection, Metropolis Hastings algorithm as well. Yeah? Right, and in any case, this is the error that we always get, regardless of the underlying dimension, regardless of everything. That was always the error in the approximation of Sn towards the quantity that we're interested in. So the difference between Sn and that integral is always 1 over square root n. Dimension simply disappears. That's the magic of Monte Carlo methods. And there were also these infamous quasi-random numbers that have this sort of error rate, which appears to be better, but also only in low dimensions. Right, and we've seen further things, in particular variance reduction. Methods to improve this, not the rate of convergence, but the actual error, which depended on the variance of the problem. This was just a recap. So these two methods we have seen. Now what's the connection? How to use Monte Carlo methods to approximate the solution of this PDE. And in order to do that, I need to introduce one important concept in, well, probability theory, which is the conditional expectation, conditional densities, or conditional probabilities, which, if you have any background in stats or math-related fields, you have seen. So what I will do is I will just try to explain it as simple as can and as needed for our setting. Yeah. But it will be I will start very simple. So remember, if we have a random variable, and here it makes sense if you've never seen this, just to think about discrete random variables, that's much easier. If you have a discrete random variable x, so for instance, the outcome of a dice, you would have a state space, sample space of 6, yeah? And the expectation would then just be the average. So P of Si would just be 1 over 6 in this case of the, well, dice, a fair dice at least. And events, the notion of event are subsets of omega x. So for instance, rolling an even number, if you were to write this down, so this guy, this is just yeah, and you can compute probability of events, of course. Like probability of that, which that set here would just be 1/3. Okay, for continuous random variables, same story. Now you have a density instead of just the probability of points. Every point, of course, has density 0, probability 0. So if I ask you what's the probability that a normal random variable hits 100, the value 100 exactly, it's always 0. Whatever value you choose, you always need to talk about, well, something like intervals, subintervals. But the crucial point comes now. Conditional expectations are the mathematical way to formally introduce additional information. Yeah. So how you can think about this is very intuitive. So for instance, if I ask you what is the expectation of, if I roll a dice, what's the expectation? The average outcome. And well, you would do a mini calculation and see it's 3.5, like average of 1 to 6 divided by 6. But that will change if I give you some additional information. So suppose this conditional expectation is the answer to, for instance, this question here, what's the average outcome of a dice? If I already tell you it's even, that's an information that you're given. So that's here encoded in the set G, or whatever, like the conditioned, this line always refers to condition. And in that case, the answer would change. It would be 4, yeah? If you think about it intuitively, at least. Yeah? We will see how to actually make this rigorous. Okay, same thing also for, well, continuous random variables, where again you need to condition on some, say, intervals or some events with positive probability. Now the crucial thing is that the distribution, of course, changes of a dice. So if I tell you that it's even, then all uneven, the probability of all uneven numbers will become 0 because you know it's even, and also the height or the density or will change. In this simple example, it's sort of trivial what happens, but in general, it could be more complicated. And the way it's defined is just everything for conditional expectations is the same. It's just the sum of the, so just as for instance here, the sum of states times their probability, but the probability is now a conditional probability, and that is defined as A intersection B. So for the probability that some event A happens, given that I already know that event B has happened or will happen, it's going to be the intersection divided by the probability of B. So for instance, that's the example for the dice, I guess. So here A would be maybe, I don't know, 2. And B we have seen was just 2, 4, 6. So the probability of rolling of 2, if I already know it's even, as well, 1/3. Similar story for discrete, for continuous random variables, where it's just the probability can be expressed via the density. Okay, so I hope this makes intuitive a lot of sense. And the rules for conditional expectations are very similar, or really just what you would expect. Yeah, it's again linear, monotone, and whatnot. And if you, maybe one important condition, if your observation, which we will use later on as well, like if you condition, say that you have two random variables and you take the expectation of the product, but you condition already that you know on one of them, the outcome of one of them, then all of this, what you know, you can take out of the expectation because it's not random. Yeah? So we will use that. That's maybe one property that is also very intuitive, but you need to think about it for a second. Oops. Okay. Now, well, okay, I guess that's just the formula for the density. But now, coming back to our course from this mini detour to conditional expectations, what we want to apply it eventually to is the solution of these Black-Scholes SDE, PD later on as well, but this SDE. And just to recall, this here is the Black-Scholes SDE, or log normal Brownian motion. S0 is just something given. And what we've seen is that this differential equation has a closed form solution, where, because this is like the final lecture, I want to highlight this once again. So in contrast to what you would naively do, or what you would naively expect from deterministic calculus, where you would not have this correction term with sigma here, for this Ito equation, you will have this additional term here. Okay, but that's just what we're given, the log normal SDE. And now what we're going to do is the following. We will introduce, well, T0, that's just the start of time. Capital T is the maturity, as always. Yeah? And that's what we're interested in, like an option on the date of maturity that depends on ST. And at the same time today, or any intermediate time, a small capital T. And what we will use a lot in the next slides is the conditional expectation of, well, ST or functions of ST given the information that I've collected until now. So what does this expression here mean is I'm conditioning on the entire past of the past, so I've kept track of all the changes in the stock from, well, the beginning of, well, my time until today. I've written them down, I've kept track of them, and now I'm going to use, well, I want to compute, say, the expectation of the stock at maturity. And I'm going to use all this information that I have collected. So from today, from yesterday, from the day before, and so forth. Clear? Okay. Now, one very cool thing here about these processes that we are dealing with is the following. They are Markov processes. And the way to see it is here, fortunately, very, very simple. Yeah? And it's maybe let me write this down actually. So this was the solution to the log normal SDE. Yeah. Mu times mu minus sigma squared times capital T's plus sigma Brownian motion at T. Yeah. So what I'm doing is, maybe let me add this here as 0 exponential of mu minus 1/2 sigma square capital T plus sigma WT. And what I'm going to do is simply do a trivial, like insert, add a zero essentially, by just writing capital T as today plus the future increment, and very exactly the same for Brownian motion. So this is WT plus the increment from today to maturity. Trivial reformulation. I've just written zero. I've just written down zero, plus zero, essentially. Now, exponential, the exponential tensorizes. Means exponential of a plus b is exponential a times exponential b, and that's exactly what I'm using here. So I collect these two terms t and this term t in the first exponential, and I collect these increments in the second exponential. Just, yeah. Now, exponential tensorizes, so it's the product of these two. And what I realize now is this first term is exactly the solution at time t, small t. That was the solution. Yeah. So this term here is just st. Second term I leave as is. So what does it mean intuitive, or in words, not intuitively? In words it means S at maturity. I can write it at S today times an independent log normal distribution. Yeah? And independent here is the crucial word, because I know Brownian, this was the defining property of Brownian motion, essentially, like one of the two defining properties of Brownian motion, that increments, future increments, are independent of the current state. So just because I know what S or what W has done until today, I know nothing about the increment, the difference between tomorrow and today, whether it's going to be positive, negative, anything. Right, and what you can follow, what follows from this, well, just trivially rewriting the process, is that if you now, for instance, have any function written on S at maturity, f of st, you condition on this whole trajectory. You've kept track of every second movement of the stock in every second. You want to compute the expectation given all this information. It's the same thing as if you just condition on today. Yeah? So this is called the Markov property, or S would be called the Markov process. Yeah. And so who here has already heard like Markov processes? Who has heard martingales? Okay, nice, that's better. Cool. Okay, but Markov property, we'll come back to martingales in a minute. But Markov property is, it's a cool thing if you think about it. Okay, so it tells me like I can forget all this information, but if you think about it practically, what does it mean? If you end up using these expressions in some further calculations, as we will do, then in principle what you would need to do in order to, well, this is a function that depends on all previous times. So if you discretize it intuitively, what you need to do is discretize the whole entire past, which is a huge discretization problem. Yeah, you need to discretize, if you, I don't know, if you do 100 days, you need to discretize 100 times the state space R even, and it will be a like exactly the same curse of dimensionality type of problem that we've seen with the PDE, exactly the same. But here Markov property means you don't need to do all that, so it's much, much simpler. It's the implementation is much easier. So Markov property or Markov processes, if you have that, that's not just mathematically an interesting, or I don't know, reduces complexity mathematically, but it also reduces it in every computational aspect. So Markov property is really, really cool. And the crucial bit here was the Brownian motion, if you think about it. So, I mean, we use that these increments are independent from, future increments are independent of, well, past and today in particular. And that's why models that are built on Brownian motion are just super tractable in general. Whereas more complicated models that might be actually better models for reality are just, have other downsides, in particular, like if you lose the Markov property, it's just the implementation is just a nightmare. Okay. So this was more or less all the facts that we need in order to relate, solve these PDEs using integration, which is part of this Dinkins formula, which essentially is an application of base or conditional expectation plus Ito and the clever reparametrization. But we will see that. Good. So what the goal here is, I mean, what the first slide here does is just another final explanation or applications of Ito's formula. So we have a function f that depends on t and x. Later on, this function f will actually be a minor transformation of the v, the price process, or the value process. And x will be a stochastic process. And what we do is, if we do if you consider the dynamics of f of t and xt, what we always do is a Taylor expansion up to second order, at least in space. So that's the classical calculus, that's the new calculus, because this term here, the dxt square term in general, is not of lower order because of if we have a stochastic process. And what comes out is well, just Ito's formula. I'm not sure. So we've formulated Ito's formula only for Brownian motion, I think. And so if x was just the Brownian motion, I'm relatively sure that I've also written it for these general Ito processes. Okay, yeah. Then this slide is somewhat superficial if you remember the formula. Yeah. Otherwise, that's just the derivation. Yeah? How you derive Ito formula for Ito processes, for when the driving process is not just Brownian motion. Okay, so f at terminal time will have something to do with the payoff at maturity. Yeah? So what we're interested in is f at time t0, where t0 is now today in this slide. What is the price of this option today? What we're going to do, the first thing is we need to take conditional expectations. We can always do that. And if we take here conditional expectations with respect to the current, like here it's called x, oops. So with respect to x t0, which is x0. So I mean, with respect to the current time, then two things happen. First of all, that here is just a deterministic number. From the perspective that if I know today's value of x of the process, then that's just a deterministic number. So this is the expectation of f of t0 x0 given x0. Yeah. The second part, the second result, is that this stochastic integral disappears. Yeah. If I take expectation. If I take condition, I mean, if it was just an expectation, then that's just what we've seen in the beginning, the basic properties of the Ito integral, that on average it's 0. And we've also seen the variance, which was Ito isometry. And the same thing happens if I do conditional expectations, because this Ito integral here, I mean, it only depends on it starts at t0, so maybe, I don't know, here's t0, and I'm only interested in computing the stochastic integral over this integral where all the increments are independent, given the information that I have today. So now, if you see this formula, and remember ft0 x0 is somewhat related to the, or will be related to the price that we're interested in. And if you remember, like this looks oddly familiar. This is almost like the Black-Scholes PDE, right? So the same idea applies here now. So if I find an f for which this term disappears, because it's perhaps even pointwise equal to 0, as was in the Black-Scholes PDE when we computed prices there, then like this whole integral disappears. Hence, if I find a function for which that is true, then f0 will be the price. It will be just the expectation of here. Will be just the expectation of f. And if we've achieved that, then we will have access to all these Monte Carlo methods and so on. Yeah. So that's what we're after, computing the price as an expectation. Clear? Okay. To do that, it's actually, like, if you see the solution, it's not too difficult. It happens to be just a rescaling of the value process. Yeah? So here, let's take f, and let's consider the dynamics of S to have the R, the risk-free returns, like of the cash account, of the bank account, volatility sigma, and plug all of this in. Yeah? And we will use this specific f. So V was the solution to the Black-Scholes PDE. Yeah? Now, if we plug this f in, what we need to do is, well, compute just the derivatives of f now, which is rather simple. We know that, well, it's a product, so it's just a product rule. So for instance, the derivative in t, well, it's just the derivative in t of the first term times the second plus the first term times the derivative of v. Same for all the other terms. That's just the product rule. And hence, what we get is this, for this specific f, we get this equation. So remember f was given as such. So at t0, it's really just v of t0. Yeah. Otherwise, it's just a discounted version of it. Hence, that's just v0. That's at terminal time. I have this PDE. Now, this is just the Black-Scholes PDE. Yeah. And I know I know, or we already know, that this has to be 0. Yeah. The process V satisfies the Black-Scholes PDE. So what is the final result? It's the price of any option today, and if the stock takes value has today value as 0, it's exactly the same as if I take the following dynamics for the stock with the same risk-free rate. I compute just the expectation of the discounted payoff. Yeah. Now this is really this is a remarkable result for many reasons. Yeah? So first of all, not that it's super relevant to this course, but I think you should know, is that if you think about it, all of what we've done didn't really use anything about T0. T0 was arbitrary. So what you actually have is Vt St given St is x, and this holds for all t and x. Okay. And what this formula means is actually the following. So you have this PDE, and you can represent the full solution to the PDE simply as this expectation, conditional expectation. And if you know something about or have ever encountered PDEs, then solving PDEs can be very tricky, especially if they're complicated, high-dimensional. Yeah? So for problems where we're interested in a simple problem, just computing V at time 0 or T0. But if you're interested like in a physical problem where you actually want a full solution, you want to see how it propagates, what is the profile at different times, you need Vt at different times, the full solution. And you can do that equally, like no modifications needed at all. Like this approach gives you the full solution. So there's a really, more deep than this connection between PDEs and stochastic processes, Markov processes in particular, that is actually really used to solve PDEs. So nowadays the story has reversed. In the beginning I told you like quant finance people in the 80s just solved heat equation because that was solved in physics. Now physical solutions are derived from these Feynman-Kac type representations of PDEs. Yeah? So I think that's a very cool fact. I mean, even though if you think about it, the derivation that we've done is not really difficult. Like you can follow every step. Nothing like there's no technical, difficult detail or anything. It's the idea that you have to have. Of course. Yeah, so the idea is the novel bit. Okay, so this was maybe the first comment. PDE has turned into integration. And okay, it should be clear to everyone now that this allows us to use Monte Carlo methods in particular. Yeah? And actually here we don't even need to generate paths of the process for options that really of European type. We really only need to generate log normal distributions, because ST given ST0 is just a log normal with a certain mean and variance. Yeah, so this is very cool. That was one thing. The second is exactly as in the Black-Scholes PDE, we have used risk-neutral dynamics. And what that means is, I mean, in principle, the dynamics is maybe this slide. In principle, the actual dynamics of the underlying S, they don't evolve exactly on average at the risk-free rates R. They have some growth mu that, I mean, typically is higher than R. And so this is really how the stock price evolves in reality. And the whole point essentially of this course, or the first part of this course, was convincing you that, well, prices, if replication is possible, prices must be given by replication arguments. There's simply no way around it. There exists exactly one fair price, and if the options are sold at any other price, you can make infinite profit, always. Yeah? Right, and how this ties here, if you think about it, mu is really not known. R is known, like we know the risk-free rates, I mean almost. But mu is really not known. That's something very subjective. So if I would ask any of you what's the expected return for Apple in a period like between now and next year, all of you would give me different numbers. That would in principle lead to different prices. So it's very crucial that you do pricing under this risk-neutral dynamics, where you pretend in this mathematical model that the stock has the same average growth of returns as the cash account. And this is really, you pretend, that's not true. That's just an outcome of this mathematical model. Yeah? So this has nothing to do with reality, this process, as of this one. Okay, so this is really, this is crucial to remember. Okay, maybe just one or two comments here. So what actually happens under this risk-neutral dynamics, and maybe also this seems to fall out of heavens that you really pick R and why R and everything. But what you can actually show, or what we can easily show, is that the discounted price process S tilde t is just e to the minus RT minus T0 ST. So that's the discounted price process. And I mean, that this is a martingale. And the way you can see it is just by using Ito's formula. So d tilde st is just, okay, let's do t0 to 0 so that it's easier for me to write this down. Minus r e to the minus rt st dt. That's the first part of Ito's formula. Plus e to the minus rt dst. That's the second part of the Ito's formula. And there's no correction term because the second derivative of this function in s, I mean, is 0. It's linear in s. Yeah? So this is really just minus r. Yeah, so this here, I mean, this here is s tilde t, the discounted process. So minus rs tilde t plus rs tilde t dt plus sigma s tilde t dwt. So only the sigma term survives. And if you stare at it for a bit, so if there was any other term than R here in these dynamics, so maybe let's do it like this. This R should be exactly this R here. So whenever you have something other than RT, these two terms will not cancel, and you will have a non-trivial drift. A non-zero drift, not non-trivial. So the statement that I want to make, probably, okay, this is always sigma. This is my way of writing sigma. That's not zero. The statement that I want to make is that if within the class of these log normal SDEs, you look for the one SDE that has the same volatility, and the discounted process becomes a martingale, then it is exactly that. There's a unique one. It has to be this one. And what will be, so this is one thing. And what you will learn partly in this course and partly in some other course is that for pricing, it will always be the case that you find a measure Q under which the discounted price process becomes a martingale. That will, next lecture you will see the Gurzanov transform, which essentially is that. Yeah. And that will always be the case. So pricing will always be computed under a measure Q for which the discounted price process is a martingale. And martingales, if you've heard it, martingales are essentially fair games. Think about martingales as fair games if you've not heard of it. So pricing is under the measure for which, well, market is a fair game. That will be a result that we will not be able to prove today because that goes a bit deeper. But this is sort of the first instance where you actually see it, and you see it very concretely. Everything is, the Q is very, very explicit. It's just the same form of SDE, just with the specific parameter. In general, it will be more complicated. Okay. Sorry, a third thing that just came to my mind that I wanted to tell you here. When computing prices here, remember, V was the solution to this Black-Scholes PDE. And we've used that heavily in the proof of this fact. Yeah? Like in this Feynman-Kac, we've transformed this solution. We've computed it. It was central that it satisfies the Black-Scholes PDE. But all of this doesn't matter here anymore. So we never use that this V satisfies some PDE, satisfies anything. We only care about V at the maturity. And V at the maturity is always just the option. So if it's a call option, then VT of ST is just ST minus K plus. Yeah? So this is always equals to payoff of option. And this here is price option today. Yeah. So that is clear in principle, but I also appreciate that like V is always the solution to this PDE in this lecture notes, and maybe you think that that you need to use that here, but it really is not needed in any case. It's really just take the option, discount it, compute the expectation under risk-neutral dynamic, and that is your price. no PDE. I mean, you need to know nothing about PDEs only if you want to prove the statement. But otherwise, you don't need to know what the word even means. Okay, so now that's the recap for well, today actually. Yeah, that's what I said. So we have this Black-Scholes PDE. We can either solve it numerically, the PDE, using discretization methods like implicit, explicit Euler, Craig-Nicholson. But we can also solve the PDE, or in particular the price, solve for the price, simply using these Monte Carlo methods. And yeah, that's just two ways to solve the same problem. And the same thing, like the rate of convergence for Monte Carlo methods is, of course, like 1 over square root n, which is inferior to PDE methods, which can be 1 over n, but only in low dimensions, in 1 dimensions. In high dimensions, Monte Carlo methods will always outperform PDE methods. So it really depends on the problem you have at hand, which option for solution you should choose. Do you have any questions for the lecture until now? The material so far?
I'm a little bit confused because you said that this only depends on risk needs and dynamics.
Yes.
Yeah. So, but we actually in the real world we have that real world dynamics. So, how does we meet the gap issue?
Yeah, that's a fair question. So maybe I repeat the question. So if I understood correctly, and you tell me. So this is how mu evolves in the real world. But we don't know mu, of course. You just can guess what mu is, but you don't know. But if you calculate a price of an option written on that stock, we have seen that to calculate it, you use replication. You can always replicate it, right, using the portfolios. And what came out of this theory is that you can calculate this price, just the price, using this expectation under the risk-neutral dynamic. That is just a method to compute the price.
So mu doesn't actually matter.
Mu doesn't matter, exactly.
Yeah. Just through calculate, there's the gap very big. We don't have to care about mu, and we can only use the replication to use the replication. Then mu doesn't matter, and we can just use R, right?
Exactly. So that's spot on. Mu doesn't matter for pricing. The drift of the stock, I mean, it would matter if you do something like utility theory or anything like that, but if you just compute prices based on hedging and replication, then mu will never enter the picture. Mu is always irrelevant. And I mean, this might be a bit confusing, I assume, or it would be confusing for me. But if you think about it, like if mu is really, really high, then still the price of the option, you can still replicate the same option by just buying the stock today. Think about it, okay, it's a very trivial example. The option is just a stock. The payout is just a stock, no call option, nothing. Even if mu is very high, what you do is you buy the stock today, you wait a year, and you get whatever S gives you. So mu is irrelevant in this example. Right. And it's irrelevant, it turns out it's irrelevant for every option. Yeah. So that gives you, okay, maybe also like this, so you can actually implement it. If you were to calculate it under the real world dynamics, you would be stuck. You would need to estimate mu. Different people would estimate it differently, get different values. There would be all sorts of problems.
Mu actually gives us the information about the stock in the long term, but when we do pricing, we only need what's today and the K stuff like that. So the information in the long term is not useful.
I'm not sure if if I would state it like this, because like if you think about it again, take the example, you have an option that just pays out stock. Option is just linear. You wait 10 years. The value of that option is just the value of the stock today, because you can buy it for the same amount of money. So I'm not sure if it's a short-term phenomenon. It's more like if you calculate prices based on replication, then just the drift disappears, the actual drift, the real world drift.
I think I'll figure that out.
Okay. Yeah. Okay, so what I would suggest now is we take, unless someone has another question, we take a 10-minute break maybe. After that, I'm going to give a recap, what I believe are the most important concepts, at least from the first 7 weeks. That will be short. And after that, you can again ask questions, either hopefully in public, because honestly, like I think if you have a question, then it's very likely that someone else has a very similar question, so it would be beneficial to everyone to ask them in public, but otherwise I'll stay here and you can ask questions like that. So 10 minutes break until 2010. Okay, okay. Um, okay, first a short recap of the course, of the first half of the course. And it's really just the most basic concept. So I think, what do I want to say? So I think what I'm telling you now, it should not be news for you. You should hopefully know all of this, or most of it at least. Yeah. But this is really just a sanity check, I guess, if you've missed out on an important concept or not. So there was essentially 5, including today 6 topics that we've discussed. I mean, I'm not going to recall today. But yeah, so firstly pricing, then the binomial model. That was the simplest model where we actually computed prices. Then stochastic analysis, this new calculus for continuous time. Black-Scholes, which was built on in continuous time, log normal SDE, and numerical solutions. That includes Monte Carlo methods. And so the pricing in this course, always there's one theme, and that theme is if you have a replicating portfolio, then the price of any option is given by the cost of the portfolio that is used to replicate it. If there are multiple replicating portfolios, they will give you the same price. And the reason for all of that is always no arbitrage. So if someone would sell it to you for less, you can just replicate it, buy it, or sell it, depending on if the price is more or less. I said less, then sell it, I guess. And just make deterministic, like profit without any risk. So that's arbitrage. In the very first lecture, if you've seen, like for deterministic payoffs, which was essentially just going from one currency to another currency or things like this, it's extremely simple. It's just discounting. So the prices are just given by discounting. For random payoffs, like options written on stocks, for instance, like this call option, it's actually absolutely not clear that replicating strategies exist. Yeah? It's still true that if they exist, then the prices must be given by the cost of those portfolios, but it's really not clear at all that they exist. We will come, maybe I'll give an example in the next slide, but we have seen in all our models, like the binomial model, the multi-period binomial model, the Gaussian model, we don't see this, but the log normal model in particular, like Black-Scholes, we always have replicating portfolios. But this is a really result, like for these models. Yeah? Good. There are, by the way, more advanced models, like more complicated models, where you do not have replicating portfolios. You will only have super and sub-replicating portfolios that are either larger. That gives you a range of prices. For more complicated models, you will not have a unique price, actually. All these prices are arbitrage-free. That's just a side remark, maybe. Okay, so in this binomial model, we have seen that, well, here, if S, the stock starts at 0, cash maybe is also 0. The model was it either goes up or down by essentially fixed quantities, fixed fractions. Cash account evolves just deterministically, and if you have any option, then you can replicate it using, well, buying or selling the cash and buying or selling stock. And if you do that, or we have done that, then you see that the price is actually given by this, well, expectation. Very, very similar as today. You realize the same formula as today almost. The same structure at least. It's discounted. You change the probabilities a bit from P to Q. Coincidentally, this was called P, but it should have been called Q somehow. Yeah, so this is Q. and you compute under this risk-neutral measure the expected value of the discounted payoff. And in this model you have also seen, or this model also shows you that replication is not always possible. And I told you in complicated models it's not possible in general. And complicated here would mean even if you add a third possible state for the future. And because then you would have 3 requirements and 2 unknowns, like stock and cash. And that's just, you cannot solve it in general. Yeah? It's not well specified. So complicated can mean like 3 lines instead of 2. Okay. And we've also seen, or yeah, you've seen it in the exercise actually, that if you refine this binomial model, meaning run it iteratively over increasingly shorter periods of times, it actually approximates, depending on the choice of parameters, but like continuous time prices fairly well, which was sort of this, along the lines of these limiting results that you have, how did I call it, Donskir's theorems, I guess, so that Brownian motion is approximated by discrete random walks. Okay, this was discrete time. In continuous time, we were exclusively dealing with Brownian motion and SDEs written on Brownian motion. Brownian motion had 2 defining properties. So it was a continuous process also, usually starting in 0, but that's really, it's a continuous process. And the increments have a normal distribution and are independent, meaning that we've discussed this today many times. So the increment to the next step is just, doesn't care about what the entire past. Okay, and then we have seen that actually, yeah, portfolios or hedging strategies, if you want to write them down, it's actually boils down to defining or computing stochastic integrals. So this would be the cumulated sums, gains and losses of trading according to the strategy, trading strategy, hedging strategy F. So we need to understand stochastic integrals, and we need to understand dynamics of functions of, well, Brownian motion. And these could be SDEs, but portfolios, whatever that we've done in this lecture. We've done all of that. The difficulty being that the Brownian motion as a function in time is just not differentiable. And if it were, we could just use classical, how's it called? I don't know, classical calculus, if you use differentiate concatenation of functions. I forgot the name, but you all know what I mean. We could use classical calculus, but we cannot because this guy doesn't exist, but we still were able to show 2 important things. First of all, that the stochastic integral always exists as long as f is reasonably well behaved, like bounded or not crazy. And it's just given as before by this Riemann sum. Which still a priori is not clear at all, because these increments, if they would all add up in the same direction, then you would never be able to define this integral. But as it turns out, the underlying reason is that there's a lot of cancellation by independence of the increments. And hence all of this argument works. You can define integrals. And crucially, well, much more importantly for this course, I guess, is Ito's formula, which I told you many times you should know by heart. It's not that complicated. Yeah, it's just classical calculus that would sort of give you classical calculus, and you have this additional correction term which involves the second derivative, which is just this weird phenomenon that for first derivatives, if you have a stochastic process, you need to know second derivatives. Right. So this formula, please remember it. I mean, for instance, for the midterm, I know like you can bring lecture notes. It's written there, but by remember, I also mean like maybe practice it, like run a calculation for something a couple of times. Yeah. So for instance, if you do the square, what you see is, well, you can do all of these calculations. There's no t, so this term disappears. X, it's just this guy, 2w, 2 times the identity. Second derivative is 1, so you just get the deterministic integral from 0 to 1, from s to t. Okay, so based on Ito's formula or stochastic integration, we were able to analyze the Black-Scholes framework, in which the price process follows the following dynamics. We have this real-world drift rate mu, we have volatility sigma, and what we've shown is this famous, or the derivation of this famous Black-Scholes formula, namely that the price process of an option evolves as follows. It must satisfy this PDE, and that gave us a way to solve for prices. And actually, it also gave us a way to compute hedging strategies, so the replicating strategies, the portfolio. If you remember, the portfolio was like this delta hedge. Right, so this PDE is very powerful. It gives you prices and portfolios. And the way we we derived it was by combining two things, actually. This was very cool. One's Ito's formula for the stochastic analysis part, and then a self-financing argument for the portfolio part. Self-financing simply meant that, I mean, you start with some amount of money, you choose a portfolio, you run according to this portfolio, and if you decide to rebalance a portfolio, meaning like a different amount of shares in cash and stock, you need to do it in a way that is self-sufficient. So no one is going to give you money, and you are also not just throwing away money. Right. Then there were also terminal. Yes? Aha, okay.
Can you explain why we do delta hedging while deriving the Black-Scholes equation?
Why we do delta hedging? Okay, let me see. It was week 4. That was. Okay. Okay, so right. What we've done is we've pi was or delta and psi. This is psi. Was just the portfolio that we've picked, and it was not defined yet. It was just the names of the portfolio, and what we need to do is we need to specify that. So CT was the value of the portfolio, and we wanted it in a way so that, well, at terminal time at least, CT is equal to VT, and in fact we said, well, let's try and aim high and see if we can replicate it throughout this whole period. Now what we've done is we've computed the dynamics of V, so the price of the option process, and that has the following form. Yeah. Now we've computed the dynamics of the portfolio, which had the following form. That was Ito's formula, and this was the self-replication argument. And I claimed that, or I claimed, and I claim now again, that that specifies delta. Because if, I mean, okay, here, I'll try with the laser pointer, and if it doesn't work, then you tell me. So if this whole thing here has to be equal to this thing here, or minus this thing. Then we've collected, first of all, we have this dt term here, then we have another dt term here, a db term, which is a dt term. Yeah? So all of these three terms were just deterministic. And the only random term was this ds term. And if you think, what this means, like if you fix time, t, and ask yourself what happens in the next tiny, tiny period, so t plus epsilon, then all the dt terms will evolve like epsilon, plus minus epsilon, but only the ds term will evolve like square root epsilon. Yeah? So all the evolution of the dt terms is like tiny, tiny, tiny compared to the ds evolution. Yeah?
In a way, it's related to the stability.
The stability of S maybe, so the fact that S is very rough. Maybe let me try to draw it. Wait, okay, I will do it the following. So, so what you have, okay, let's do it in a following way. So we want 0 is equal to a dt plus b dst or dwt. This is actually, if we rearrange these formulas that we had here, okay, if the sum of them has to be 0, I collect all the dt terms, I collect the ds terms. Okay. I'm not used to this computer. So now if you have t and t plus epsilon, then this a times whatever will evolve like this. This will be like a times epsilon, so the difference. Yeah, but this here will be b times square root epsilon. That will be the ds term. Yeah? And it will be random also. Yeah? So this, whether it goes up or down, it's random. So that means there's no way to correct it using A. If the B term is non-zero, then this whole thing cannot be 0. Formally, if you want, what you could do, but this is only for people that have heard some probability theory. What follows from this equation is, of course, you can take quadratic variation. 0 plus b squared dst. And I mean that is like dt. So b has to be 0. That would be the mathematical argument.
And the economic reason why we do that, is there any?
Is there an economic? There might be. I mean, probably there is a reason. But I cannot give the reason now. I mean, the proportion of stock is depending on the marginal value increase or decrease. I mean, this is what it says now. But I really don't know how you could make a proof that is out of it that is just based on economic reasoning. Probably you can. I mean, yeah.
Maybe not reason, implication.
Yeah, I mean, implication is that the solution of the PDE specifies the hedge. Yeah, because delta must be the derivative of V. So if you have the PD solution, you also know the hedging strategy. Yeah, but it comes out of this math argument that delta needs to has this specific form. Okay, everyone satisfied? Okay, let me go through the next slide, and then we come back to terminal and boundary conditions.
Just a tiny question.
Yeah, sure, yeah.
So, is it possible for us to take the sort of same log normal dynamics that we are considering and do different steps and arrive at a different model?
At a different model means.
Like not Black-Scholes model, but like some sort of different mathematical equation that those dynamics might satisfy.
So what you could do is you could just try and run the same argument for just plain Gaussian SDE. Not exponential, so we're not the returns are Brownian motion, but absolute values.
Okay, so like the other way to say it is, if we have a given, like for example, log normal dynamics for the stock prices, it has to follow this particular Black-Scholes theory, right?
Yes, there's no way around it.
There's no. So
Yes.
there is a one-to-one mapping, or like what underlying dynamics we're considering and what model.
Yes. If you model you mean PDE, then yes.
Yeah,
So
yeah.
underlying the dynamics specify the PDE. Yes, so this is the Black-Scholes PDE. There's not Black-Scholes PDE 2 or 3. It's the Black-Scholes PDE. Okay. I might see where the confusion arises. Maybe it's because of the boundary conditions. I told you that there, in principle, are many solutions to this PDE if you don't specify the boundary conditions correctly. That is just the mathematical nonsense somehow, like abstraction that you need to take care of, but that's not really it. That's very irregular solutions. Okay, so for numerical solutions, we have seen two methods. Four, actually, but like two groups of methods. The first was discretization of the PDE. That's also the one that you've implemented, which was setting up grids, either doing forward or backward, forward or implicit, or a mixture of those methods. So these were and Euler methods or these Craig-Nicholson methods. And all these methods had certain advantages and disadvantages. So explicit Euler was just really, really simple. It was just one step forward in time, and you always use approximation of different gradients, but one step in time forward, you didn't need to solve. It was just a matrix multiplication that you needed to solve for the algorithm, so very simple. But it was not stable, and it was relatively slow, the rate of convergence, at least in comparison with the Craig-Nicholson scheme. But for Craig-Nicholson, you need to invert matrices, essentially, which is computationally more challenging. Yeah? But it was stable, and stable means unstable. Let me say it like this. An unstable method means you really need to think about it, about the specific problems, about the specific parameters for discretization, specific to your problem. Do they make sense? Are they suitable or not? If not, the solution could blow up completely, meaning that the error would be really extremely, extremely bad. So stability or having a non-stable method comes at a very high price. So you rather strive for stable methods, which would be the Craig-Nicholson. And finally, we have seen today that by risk-neutral pricing, these prices, or effectively the whole solution of the PDE, can be obtained through just taking expectations. and thus using sampling. So this was the idea of Monte Carlo, approximating expectations using Monte Carlo, and just because I was asked this also. So yeah, unfortunately in orange, yeah, forgive me. But what you would end up doing if you would compute these prices, of course, are, I mean, here use Monte Carlo, just generate IID log normals, yeah, IID log normals, these YIs using whatever method you want, inverse, I mean, you don't even need inverse transform here. It's just exponential of a Gaussian. And just take the average. And that will convert you to the price of the Black-Scholes price of your option. Okay, and these methods are in particular suitable for, we've seen various ways how to generate random samples. And in general, these Monte Carlo methods are very suitable if you have complex payoffs. Complex can mean many things. Here it means just high dimensional, like options that depend on like maybe 10 stocks, the sum of 10 stocks, some complicated options on 10 stocks. And also if they're not really super regular, like if you have an option that is not super smooth, Monte Carlo doesn't care. PDE might care. Like PDE is something about differentiations. So if you have a non-differentiable function, you need to take care of it and see if it really works and so forth. Monte Carlo really doesn't care. Yes. Okay, before I go into, like I was asked in the break to explain again a bit the boundary conditions for the PDEs, the numerics. Maybe before I go into that, let me say, so you all know hopefully that I mean the midterm is not taking place now, but it's taking place next week. At this very time, or not this very time, at 7, in the multi-facility sports hall. I forgot, there's an acronym, as for everything. That is not here, that is like 15 minutes away, I guess. And you should be there a bit before 7, because like it will start at 7. We maybe have a couple of minutes, but not too long. So please be on time, and as I wrote, like you can bring lecture notes. I mean, lecture notes means these lecture notes on Canvas. So I wouldn't recommend printing out all the slides, to be honest. I mean, it's not, I guess, yeah, it's neither, like, it's not the lecture notes, but I would also not recommend it. The lecture notes suffice, definitely. It will be only until the Monte Carlo methods, and they're also not really the second part. Like I will not ask you to explain Metropolis Hastings or anything like this. Yeah. Right. So my idea for the midterm was actually probably the same way as has been the last years, is to do just a checkup with you if you understand the basic concepts. And by basic concepts, I mean more or less the questions that I've explained here, or the concepts, like just broadly if you've understood what this course is about. So yeah, it will be multiple choice, I don't know, 15, 20 questions. You can imagine you will not be asked to do crazy calculations in a multiple choice exam. In my opinion, you don't need to worry too much about this midterm. The final exam will be more like the exercises as well, like including like coding and algorithms. This multiple choice will really just ask basic questions. If you follow this course, you should know all of them. Yeah. I'm not sure how dissatisfied you are with this change of format. I was quite annoyed because like it was the case always, and now they changed it effective immediately, even though we've already fixed sort of the setting. So I tried. I just want to let you know I tried really hard. I went all the way to the provost's office to try to get an exemption for this course to make it this 1 year in the same format that it has been before, but unfortunately no. So yeah, that's why next week we will have the midterm in person. But still, you bring lecture notes, the one handwritten piece of paper if you want, and yeah, if you have any questions about that, you can also ask. I just no calculator needed and no calculator allowed. Thank you very much. 15 to 20 questions, multiple choice. One correct answer in each question. Okay, so what I would do now is explain once again the boundary conditions. That will not be super relevant for the midterm. Still, like in the finals, and you will need to know it. And I was asked in the break, so I will explain again the concept and how to come up with these boundary conditions, and then you can ask another question. If there's other questions, then I'm going to answer them. So for these PDEs, what we've done is, so unfortunately, or let me just start from scratch. So what we've done is we've set up the grid in the following way. Like this, okay? That always t was here and 0 was here, but we've always reparametrized the PDE. So that means this is maturity. Simply by essentially taking T minus T instead of VT. That will just give you a forward instead of a backward PDE, which is more in line with what people in physics have done. Yeah, so it starts here with S min, S max. We've chosen some like very large and small values for S min that are the boundary of our grid. And we have an option, I will call it C of x. Yeah? So the first thing that we've always knew is that V of Tx is just C of x. Because, well, the value at maturity, if I know that the stock is exactly at x, I get paid C of x. And there's no discounting happening because, like, I'm at maturity. Like, from the perspective of maturity, the value has to be C of x. So that means, like, here, here I will always have C of S min. I don't know what this is, maybe S1, S2, S3, and so forth. I will always have C of S3, and so forth. all the way up to this node C of S max. Yeah. So this bottom line, it's always given. It comes just from this fact. Yeah. And this is this condition is the natural condition. That's the only natural conditions of the three, arguably. That just says, well, the value at capital time has to be equal to the payoff of the option. Yeah? But what we needed to do additionally is specify other boundary conditions. Because we have a PDE of third degree, we have three sort of derivatives. You can think of this of like having three equations, and we needed to specify one. There are many PDEs that will satisfy that. Just as if you have a system of three unknowns and one equation, then it will give you a family of parameters feasible. And the same thing happens for the PDE. So there are many PDEs, and in order to specify PDEs that are nice, and nice means for us they satisfy all these properties that we have used for stochastic integration, for here's also nice, F nice. Yeah? For all this maths that we've done, you can imagine that this breaks if F oscillates like crazy. If F is super unbounded, then these methods will not work. So think of these boundary conditions as specifying regular solutions. And the boundary conditions we need to specify at the boundary. So this is the unknown. This is what we want to know. Yeah, so this we cannot specify, this boundary. So what we need to specify is this boundary here and this boundary here. And I will do that in one example now. Yeah, that's readable, I guess. Let's do it for the call price, for a call option. Okay, so we have seen actually that there are two sets of boundary conditions, Dirichlet and Neumann conditions. Dirichlet was considering absolute values. Neumann was considering marginal values. Yeah. Arguably, for call options, actually Neumann conditions are easier. So let's do the Dirichlet conditions. Maybe Dirichlet first. So if I ask you how to compute the boundary conditions here, what do these boundary conditions, what do they mean? Yeah. So V at time small t of x, where x is actually S min. This stands for the value that I will assign to this call option if at time t the price is extremely low. And S min you can think about zero essentially. So the price it's lost. The stock is bankrupt almost. Yeah? So if you are thinking about what the stock is bankrupt, it will probably not recover. Hence, there's almost no chance for the stock to go beyond this threshold K. So there's almost no chance for this option to pay out anything. Yeah? So it will be zero or almost zero. Yeah? So here it's almost zero, and that's regardless of the time. So even if I have like 9 months to run and the stock is bankrupt, almost bankrupt, it will not it will not be in the money at the end. So here I will always get 0, 0, 0, 0. Yeah. How does it look on the right side? There it looks a bit more complicated. And maybe to explain this is best to think about today. So say t is a year. I have a horizon of a year. Yeah? And just think about it for yourself. What is the value of this call option with, say, strike price 100? Yeah? And I have a stock price that has normal volatility, like a couple of percent. And the stock price today is a million. What will be the price of this option? So I'm pretty sure that the stock will be in the money. It will move by 5%. It will not move by like 99.999% down. Yeah? So I'm pretty sure it will be in the money. So what I get is I must pay K at the end for sure. So what I will get here, oops, let's make it like this. Yeah. So what I will get here is certainly K minus K, but this will be discounted because it's in the future. So K minus e to the minus RT. And however, I will get the money from S. So S will be paid. So it will be actually S or X, S max. And that will not be discounted. And the reason is, I mean, I could just take this money as zero now and invest it in the cash account, and it will grow at exactly that rate. That cancels discounting. So the value is S max, not discounted. But K has to be discounted because K, that's just a fixed amount of money that I need to pay. Yeah? And in the same principle, so you would have X max, K minus e to the minus R, capital T minus T. Okay, so these were the Dirichlet boundary conditions. Neumann boundary conditions concern the marginal gains. Yeah. But this is a chaotic slide. I already see it coming. So this is Dirichlet. Let's do Neumann. Same argument, so if the stock is already bankrupt, it will increase 1 unit. It's still very far out of the money. I will still get paid nothing. So here I will always have delta V of T S min is 0 or approximately 0. If it's very much in the money, like a million, and it changes a bit, it will stay in the money very likely. So the marginal gain at the right boundary condition, it should be just 1, like the slope of stock increases by $1, I get paid out $1 more. Any other questions? Yeah, we can also call it a day, and I'll stay here again for a bit if anyone wants to come forward and ask something. Otherwise, yeah, see you next week. Yeah, good luck already, and yeah, have a nice evening.
Can I ask for one follow-up? You mentioned that the convergence is square root s regardless of the dimension.
Yes.
But will there be extra time compression for generating n dimension?